So this lecture is about double negation translation and Cps translation. We are going to investigate the relation between classical logic and constructive logic. So previously, we derived the classical logic as an extension of constructive logic. So from constructive logic, we can add a new axiom, for example, this law of excluded middle. Then we obtain this classical logic. Or alternatively, we could add, instead of this law of excluded middle, we could add another axiom, double negation, elimination, or Peirce's law. But in any case, classical logic is obtained by augmenting this constructive logic with a new inference rule. As a result, in classical logic, we can prove more truth judgments than in constructive logic. So for example, if you can prove, say, C true in constructive logic, you can definitely prove it in classical logic too, because it is classical logic inherit all the inference rules from constructive logic. And moreover, you can prove more truth judgments than constructive logic. And the most representative example is this axiom, this law of excluded middle, which is not provable in constructive logic, but is definitely provable in classical logic. So in classical logic, so we have classical logic and constructive logic. And if we move this direction, we can prove more truth judgment. And if we move this direction, we can prove fewer truth judgment. And we might think classical logic is more powerful than constructive logic because it allows us to prove more truth judgment. But it turns out that to be able to prove more truth judgment should not be equated to being more powerful. For example, in the extreme case, we could consider a funny logic where bottom true is provable. In this case, we can prove all the truth judgments out there. But clearly, this logic is useless because we can prove everything. So from this spectrum, we can anticipate that constructive logic is perhaps more powerful than classical logic, or more expressive than classical logic. And in fact, constructive logic is more powerful than classical logic because we can simulate classical logic within constructive logic. So in some sense, this constructive logic can make fine distinction between truth and falsehood. In classical logic, we have only two states for every statement. It's either true or it is either false. But in the case of constructive logic, we also consider this middle state. So that's the relationship between classical logic and constructive logic. Classical logic allows us to prove more truth judgments than constructive logic, but that does not mean that it is more powerful than constructive logic. In fact, constructive logic is much more powerful than classical logic because we can simulate classical logic with constructive logic itself. And this lecture is about how to simulate this classical logic with constructive logic. And the technique we employ is what is called double negation translation. Double negation translation. So let's see how this translation goes. So the idea is, so here we have classical logic, and here we have constructive logic. And the idea behind this double negation translation is, so we are going to show this double negation translation. We'd like to translate a proposition or formula A in classical logic into a circle. And later we will show that if A is true in classical logic, then we will show that double negation A circle is true in constructive logic, which intuitively means that when you are saying that A is true in classical world, from the viewpoint of constructive logic, it's really it really says it can't be false. It's double negation. It can't be false. So that's the view from this constructive logic. In this regard, we can see constructive logic can make a fine distinction between truth and falsehood. So this is the plan. For every formula A, we are going to give a translation of, it's a translation in constructive logic, which we write as a circle. And later we will show that whenever A is true in classical logic, a double negation, A circle is true in constructive logic. So that is, when you are saying A is true in classical logic, from the viewpoint of a constructive logic, it is A can't be false. And the translation is almost structural, which means that, for example, A conjunction B is translated to A translation conjunction B translation. And A disjunction B translation is also structural. A circle disjunction B circle. And top is translated to top, and bottom is translated to bottom, and atomic proposition is translated to atomic proposition itself. The only exception is this implication. A implies B. So the translation of A implies B is A translation, A circle implies double negation B circle. So it turns out that the key idea in this double negation translation is found in the translation of this implication. So let's see more carefully. Let's analyze more carefully this translation. So in classical logic, we have A implies B, and this is translated to A circle implies double negation B circle. So this is the interpretation of classical function. So this is, say, classical function or function in the classical world from A to B. So the classical function of type A implies B is, from the viewpoint of constructive world, it takes an argument of type A. So it takes an argument of type A, and then it returns this one. And we can expand this one into negation B circle implies bottom, or it means B circle implies bottom implies bottom. And this is a type of a continuation of type B. So this is a continuation of type B. So what that means is that you have to first provide an argument of type A circle. Okay. In the case of a classical function, if you are given an argument of type A, you are supposed to return result of type B immediately. But we don't return a value of the result of type B right away. Instead, we take some different action. And it is, I expect you to provide me with a continuation of this type. And then I will compute the answer myself. So the best way to interpret this bottom is answer. Answer over some computation, the final answer over your computation. So what that means is that first, give me an argument of type A circle. Instead of returning the result of type B circle, I need you to provide me with a continuation of this type. That is, this is basically what to do with some result of type B circle. So I refuse to return the result of a type B circle right away. Instead, I would like you to provide me with what to do with the result of a B circle. Now, what happens is, from an argument of type A circle, I produce result of B circle, type B circle. And you have told me what to do with the result of type B circle. So I combine these two. So I carry out the action myself, and then produce an answer of a type this bottom. So the computation process is indirect way, in the sense that instead of returning the result of a B circle to the caller, I take the action myself. So first, provide me with the argument, and then I compute the result myself. And then, but you have told me the action to be taken with the result. So I take my action. I take the action myself. I carry out the action myself, and then return the answer. So that's the intuition behind, the informal idea behind this translation. The key point is, in classical world, you'd return the result of type B immediately. But in the case of this double negation translation, you never return the result of type B. Instead, you carry out the action that is what to do with the result of type B. And you carry out the action yourself, and then you just produce the answer. That's all. So that's the reason why this thing, function of type B implies the bottom, is called continuation. So if you are confused about this way of looking at this type, you can think of this one as return address. Return address expecting value of type B. So you give me an argument of type A, and you also give me a return address expecting value of type B. So now I have an argument and return address. So from this argument, I compute the result of type B. Now I make a jump to this return address. So that's how another way of interpreting this type. So with this double negation translation, we can now show how to simulate the classical logic within constructive logic. So the plan is this. So this is classical. This is constructive. If C is true in classical logic, I'm going to show C, a double negation C circle is true in constructive logic. And in order to prove this statement, we have to generalize the statement. So if gamma delta classical logic is true, where gamma is a collection of these truth assumptions, and delta is this collection of false assumptions, then gamma translation, delta translation, this I stands for constructive. So a synonym for this constructive logic is intuitionistic. So this I stands for intuitionistic. So in constructive logic, we have double negation C circle is true, where delta circle is A circle true, gamma circle, and delta circle is negation B true. In the course notes, we use this additional symbol negation, but it's only confusing, so please disregard this negation, omit this negation symbol in the statement. So the idea is that A true, an assumption of A true in classical logic is translated to A circle true. Well, there's no surprise here. And assumption of a phi false is translated to negation be true, which makes sense because phi false means, well, roughly speaking, phi false means negation B is true. So we use this negation B circle true. Then we can show that the probability of a C true in classical logic guarantees the probability of double negation C circle true in constructive logic. So that's basically the result that we can get from this double negation translation. So now we are going to give a proof of this double negation translation, but instead of working in terms of these proofs, derivation trees, we'd like to work directly with the proof terms. So the idea is that if you have, in classical logic, if you have a gamma, delta, proof term M of type C, where gamma is just the assumption of these type bindings, and delta is assumptions of type A false. Then we can find a proof term under this translated context. We can find a proof term M circle whose type is double negation C circle. So in other words, instead of working with these derivation trees, we'd like to work directly with these proof terms. So instead of showing the existence of derivation trees, we simply present this proof term, which is okay because under the Curry-Horde isomorphism, this proof term can be shown to be equivalent to this derivation tree. So that's the plan. For every proof term M, we'd like to find a corresponding proof term M circle. And here, gamma delta is basically X has type A circle, and delta translation of delta is Y has a type negation A circle. So this is confusing. So let me write this B, and this is B. So this is what we'd like to show. And this is called CPS translation, an important technique in compiler construction. Although it's not quite popular these days, this CPS translation stands for continuation passing style. Continuation passing style translation. And as I said before, in this translation, the notion of continuation plays the key role. So negation A circle, this is A circle implies a bottom, and this is basically continuation of type A circle. And you can interpret it as return address expecting some value of type A circle, or you can interpret it as, say, call stack expecting value of type A circle, whichever is more convenient for you. So basically, this thing expects a value of type A circle, and then it carries out some computation, and then finally returns some answer. So we don't know what the answer is, so it is a bottom, but we know that there is some sort of answer. So basically, the idea is you give me a value of a type A circle, and I will carry out the computation myself, and then find the answer for you. So that's the idea behind the continuations. Now I'm going to show the actual translation, this CPS translation, which converts this proof term M into this proof term M circle that satisfies this relation. So if M has a type C, then M circle has a type double negation C circle. So the translation is not actually quite easy, but there's no surprise here. The translation, it's not trivial at all to develop the translation, but there's no surprise either. So let's consider a few representative cases. At first, the translation might seem quite weird, but after a few cases, a pattern in the translation emerges, and then you will be able to see the key idea in the translation. So let's first consider this variable case. So the first case is, so the proof proceeds by induction on the structure of this derivation, this typing derivation. So we perform case analysis on the shape of this derivation tree by focusing on the last inference rule in this derivation tree. So the first case is the last inference rule is this hypothesis rule, gamma delta xa, where x colon a is found in gamma. This is hypothesis rule. So remember that we are supposed to find a proof term x circle which has a type double negation A circle under this translated context. So we have to find some proof term of type double negation A circle. But this thing is negation A circle implies a bottom. And this negation A circle is A circle implies a bottom. So basically, you have to find a proof term which takes a function of this one. So this is a continuation. Or you can think of it as call stack. Continuation of this type and then produce an answer. So give me some continuation of type A circle implies a bottom, and now the problem reduced to finding a proof term of type bottom. So now you have to find some answer. And in this case, it's pretty easy to find an answer because now you have continuation of type A circle implies a bottom. So it's just a matter of applying this continuation K to an argument of type A circle. And luckily, we have such a proof term because under this typing context, the gamma circle, X is going to have a type A circle. So it simply provide proof term X. So this is the translation. Now let's consider this conjunction introduction case, which is actually shows the typical pattern in the translation. So the second case that we are going to look at is gamma delta classical logic M and it is type A conjunction B, and M has a type A, N has a type B. This is a conjunction introduction rule. Again, we are supposed to find, our goal is to find a proof term such that, this is translation of this proof term, and it's going to have a type double negation A conjunction B translation. And this is A conjunction B translation implies bottom. So we are going to use variable K for the argument of this type. So this translation of this pair is going to first takes a continuation of type A conjunction B translation, which is A translation conjunction B translation implies bottom. And then now you have to find a proof term of type bottom, or you have to show how to produce an answer. This is an answer. So, and the plan is we'd like to exploit this proof term M, and of course, the second proof term N as well. First, the goal is we should find an answer of a type bottom. Let's first exploit the translation of M. So this translation of M has type double negation A circle, which is A circle implies a bottom. So in order to produce a bottom, it suffices to provide a function of this type. So if you can find a function of type a circle implies bottom, then that's it. M has this type, the argument has this type. So we create a function of type a circle, and now the body is going to have a type bottom. So that means that we compute M, and then it will produce a value of a type A circle. And then the rest of computation is described here. So this is the continuation, which tells you what to do with a value. So this continuation tells you what to do with a value of type A circle, or how the computation continues with a value of type A circle. And intuitively, after computing a value of type A circle, you want to compute another value of type B. So here, the computation proceeds. I would like to compute N circle. Now, this N circle has type B circle implies a bottom. So in order to produce a bottom, it suffices to provide a function of type. It's quite confusing. So you have to provide B circle implies a bottom, or a continuation for type B circle, or how. So this function is going to describe how the computation continues with a value of type B circle. So let's just say this is lambda y dot B circle. And then this one, the body, is going to produce a value of type bottom. So this function shows how the computation continues with a value of type B circle. Now inside this function body, you have access to y, the result of computing n, and also the result of computing m, which is a variable x. So therefore, inside this function, you have both a value of type A and value of type B. So now you can construct a pair of type A conjunction B. So let me clear things up. So this is all gone. Okay. Now you have to find here answer of a type bottom, and you have access to this variable y of type B circle and variable x of type A circle, and finally you have this continuation. Now the pattern emerges again. You have this continuation. So in order to produce a bottom, so this bottom is going to be this bottom. You only have to apply this continuation to an argument of type A circle conjunction B circle, which is x and y. So this guy has type A circle conjunction B circle. So therefore, this application is going to type bottom. So now, perhaps you will start to see the pattern in this Cps translation. Instead of returning the result right away, you finish the whole computation in an indirect way by telling us what to do with the result. So for example here, you compute a value of type A circle, and this continuation tells you what to do with this result. And what to do with this result? Well, we compute n and then describe the rest of the computation. So the story goes, you compute M, and this is the rest of the computation. And the rest of the computation is, you compute the N, and this is the rest of the computation. And the final piece of computation is, you build this pair, and then pass to the original continuation. So I think the translation of this pair tells us the essence of the translation, or the key idea in the translation. Let me show you another example. This time, it's going to be the projection. So you have the gamma delta. First M, it is type A, and M has a type A conjunction B. So what is the translation of a first M? So whatever comes here must have a type double negation A circle, or A circle implies a bottom, implies a bottom. So this is the continuation. Tell me what to do with a value of type A circle. So this is a lambda K, continuation of type A circle implies a bottom. Now you have to show me how to carry out the rest of the computation in order to produce an answer. And in this case, we have to use this one somewhere. So how do we compute? Well, we have to, in order to compute this one, you the first compute M. So therefore, you compute M. And M has type A conjunction B. So in order to complete the whole computation, you only provide, so this one has A conjunction B translation bottom implies a bottom. So in order to produce this bottom, this is the same bottom, here you have to provide a function, and this is type A conjunction, A translation, conjunction B translation, and then you have to produce an answer here. Now it's pretty easy because you have a value of type A circle conjunction B circle, and from this you can easily create first M, which is the type A circle. But previously we have provided this continuation, what to do with a value of a type A circle. So you apply K to first M, then it is going to be bottom, so this bottom. So again, we see a similar pattern that we have seen in the previous translation, the translation of a pair. Next, let's see the translation of a function. So we'd like to see the case gamma delta classical logic lambda x a dot m. It has a type A implies a bottom, and the premise is M has a type B. This is implication introduction rule. And the question is, what is the translation of this lambda abstraction? So it must be of type A implies a B, translation implies a bottom, implies a bottom. Or if you are confused, it is actually double negation. A implies a B, bottom. And we can further expand it into A implies this is A implies double negation B circle implies bottom implies bottom. So for the first argument, it's going to be this one. Continuation of type A translation double negation B translation implies a bottom, and then this one is going to be the same bottom. So with the discontinuation, you have to show how to produce an answer. And in this case, the plan is we'd like to produce an answer from this kappa, this continuation K. So this is the same one, and we'd like to use this one. So it's just a matter of, so the whole problem reduced to finding a right argument to this continuation K. And the type is going to be A circle implies double negation B circle. So we have to construct a lambda abstraction of this type. So let's say this is lambda x A circle, and now you have to find a proof term of double negation B circle. But that's precisely translation of M circle under this extended typing context. That is, by induction hypothesis, M circle has a type double negation B circle, provided that X has a type A circle, which is precisely the situation we have here. X has type A circle. So therefore, inside this lambda abstraction, M circle has type double negation B circle, which is what we want. So it turns out that the translation of this lambda is just applying the continuation K with this suitable translation. And if we think about the meaning of this translation, there's no surprising thing here. It simply says that this continuation K says, given me a function of this type, then I will carry out the answer. I will carry out the rest of the computation for you and produce an answer. So I just provide the function. This is the function. So there's no surprising element in this translation. Next, let's translate this application. Gamma delta Mn has a type B, where M has a type A implies B, and N has a type A. This is the implication elimination. So the question is, what is the translation of this application? It's going to have a type double negation B circle, that is, B circle implies a bottom, So you first provide this continuation of type B circle implies a bottom. So this thing tells you what to do with a value of a type B circle, or it's the rest of the computation. And now you have to find a proof term of bottom. So you have to show how the rest of the computation proceeds. So when we compute this m applied to n, this is the first proof term that we evaluate, and then we would compute this one and then apply whether it is called by value or called by name. So we first compute m circle and then describe what to do with the result of computing m circle. So this is basically continuation that you take over the computation after m circle. So again, we compute m and then show what to do with the result of computing m. Okay, so this one is going to have a type. M has a type A implies a bottom. So M circle has a type A circle implies double negation B circle. Oh, sorry. This is double negation. So that is, it has a type A circle implies double negation B circle implies a bottom. So you only have to provide a function of this type here. So this is lambda x type A circle implies double negation B circle, and then you have to find proof term of type bottom. So you have just computed m, and the result is stored in this variable x. Now, the next step in the computation is, of course, to compute n. So the plan now is I'm going to compute n and then describe the rest of the computation. And n has a type A, so it's going to have lambda y a circle, and then this is going to have a type bottom. So the story so far goes like, I first compute the m, and the result is stored in x. And this is the rest of the computation. And in the rest of the computation, I compute the n, and then the result is stored in y. Now, whatever comes here is going to describe the rest of the computation. So what is the rest of the computation? Well, you apply x to y, and then it gives us a value of a type double negation B circle. And this thing expects what to do with a value of negation B circle. So this is confusing. So it has a type double negation B circle, or negation B circle implies bottom. So basically it says, tell me what to do with this B circle, then I will finish the computation for you. But luckily we have this continuation K of the right type. So you apply this one to K here, and then you obtain this bottom. So it turns out that this corresponds to call by value translation. The last two cases deal with the call CC and throw. So let's see. What about call CC? Gamma, delta, call CC, x, a false, m. It has a type A. If x has a type A false, and here m has a type A. This is the call CC. Then the question is, what is the translation of a call CC? So it's going to have a type double negation A circle. So it says, give me this continuation of type A circle implies a bottom. So this is the continuation. Or tell me what to do with the result of type A circle. Then I will compute the answer for you. So you have to find a proof term of type bottom. But from the premise or by the induction hypothesis, M circle has a type double negation A circle. If X has a type negation A circle. So under this extended context, M has double negation A circle. So now we have this concrete continuation of the same type. So this is the type negation A circle. And M circle would have a type this one if X has a type negation A circle. But we don't have X, but we have this concrete continuation K. So the plan now is we substitute K for X in M circle. Then this is a type, double negation A circle. Now in order to produce bottom here, you have to provide a value of type negation A circle, which is K. So this is the translation. It means that I'd like to continue the computation, and the rest of the computation is captured here. So this is basically the rest of the computation, or at runtime, the call stack, the current call stack will be stored in this variable K. So this is basically the rest of the computation. In other words, at this point, the call stack is stored in K, but the call stack is basically the rest of the computation. So you use it again here. So that's the translation of the call CC. And the last case is throw gamma delta throw m to c, m to x has a type C if gamma delta m has a type A and x a false has type in delta. So by induction hypothesis, we have gamma delta translation. M circle has type double negation A circle if x has a type negation A circle in delta. So that's the result that we obtain by induction hypothesis. Now, what is the translation of throw m to x? So it has a type C. So it's going to have a type double negation C translation, which is C arrow bottom implies a bottom. So it is going to have lambda k of type C implies a bottom. But actually, we will not use this one because we actually throw this value to x. So in this context, so this is not if actually. In this context, we have this one. Now we have to find an answer. And from the translation of M, we have this double negation A circle. And we know that X at the time negation A. So there's no need to use this one because we are ready to produce the answer. Namely, we have a negation, double negation A circle, and we have negation A circle. So it's just a matter of applying M circle to X. So that is, we compute the M, and the rest of the computation is stored in X. So perhaps the value stored in this variable X was captured earlier. So that's the way that we make this time travel to the point where X has been created with the result of computing M. That's how we translated this row.